Hi, welcome to this video on percent composition. So in this video, we're going to focus on looking at chemical formulas and understanding the composition of a chemical formula. So to review that, first thing we want to look at is some review stuff of pure substances. So we talked briefly about pure substances. We're still talking about pure substances. But last semester, we spent time talking about elements as a pure substance, right? Elements are going to be our elements that are on our periodic table. So to be an element, there can only be one kind of an atom, and they cannot be decomposed into anything smaller, right? So there's no chemical reaction we could use to break an element into anything smaller. So example of elements, you could have silver atoms, right? We can also have, let's say, sulfur atoms, right? We can also have diatomic elements, which are like oxygen. Remember O2, oxygen never exists as a singular atom element, right? But there's still only one kind of element or atom in that. So it's oxygen considered an element, okay? Then we also have compounds. Compounds are also pure substances. This is what we spent time learning how to write chemical formulas for, using ionic bonding techniques, covalent bonding techniques. Those are compounds. This is when you have two or more different atoms. That's the key. It doesn't say that on there, but your atoms do have to be different. So there has to be two or more different atoms, and they've been chemically combined either with an ionic bond or a covalent bond, either one. And so when they're chemically combined, they make a larger unit that we call a compound. So in this chapter, we're going to be focusing a lot on our compounds as our pure substances. So let's start about the law of definite proportions. So there's a couple of important laws. They're really easy to kind of understand. They're really pretty, the law is an explanation of nature, right? And so that's really all it is. It explains something that's very obvious. It should sound familiar because it's law and it's definite. Definite means never changes, right? And proportion means how things are related to each other. So a compound, let's use water as an example, right? The formula for water is H2O. So I have H2O. That is specifically the formula for water, or two hydrogens, right? And my ratio, one oxygen atom. If I don't have two hydrogens and one oxygen atom covalently bonded, right, then I don't have a compound of water. Okay, that's the key. So the law of definite proportions basically says that we must keep that proportion of hydrogens to oxygens in my molecule at all times. It doesn't matter how large or how small my sample is. So we can be talking about one individual atom, or I could be talking about moles of atoms, large quantities, swimming pools worth of water, right? Doesn't matter. So the key is that a compound is always going to have the same elemental ratio or composition, so their masses will also remain in that same fixed or definite ratio. Super easy. To be water, it has to have two hydrogens and one oxygen. It doesn't matter how much water I have, it's still two hydrogens, one oxygen for every molecule. So picture is just showing exactly that. So I could have a water bottle, I could have a cup, I could have a swimming pool, doesn't matter. The water molecule is still the same compound, so therefore my ratio of hydrogens to oxygens are the same. And that means my percent of hydrogen to oxygen by mass is still exactly the same, because if I have two hydrogens, right, in terms of mass, two hydrogens would basically be 2.02 grams per mole, right? And if I have one oxygen, then that's essentially going to be 16.0 grams per mole. So it doesn't matter if I have a swimming pool of it, the ratio of mass would always reduce to 2 to 16, okay? So then we also have this law of multiple proportions. All right, so in this law, the law of multiple proportions should sound like what it makes sense. Multiple. So proportion, multiple. All right. So what this one says is that a compound's elemental composition is still always in that fixed definite ratio of whole numbers. Different compounds can have the same elements, but they still have their own fixed definite ratio, okay? So it just means that two elements can have different ratios, but that makes them different compounds. So I like the example of water and hydrogen peroxide, okay? So individually, oh, I messed that up. So individually, water, hydrogen peroxide, right? When I look at these, I have water. We know water is not the same thing as hydrogen peroxide. And I'm just going to add this joke in there. So hydrogen peroxide, I'm going to preface this so you understand. Hydrogen peroxide is not something as a human that we would want to drink because it is poisonous to us. And so there is a joke where a man walks into a bar and he orders a water or an H2O. He says, I want an H2O. And the bartender gives him an H2O. Another guy overhears him and says, I also want an H2O too. Well, he dies because he ordered hydrogen peroxide. Okay, so I know, super cheesy, really dorky, but whatever, it makes me laugh. I love the cheesy chemistry jokes. Okay, so the key here with the law of multiple proportions is both of these have the same elements. That's what they mean by multiple, okay? So there can be multiple proportional ratios between two elements, but those proportions are going to vary depending on the compound, all right? So water specifically is 2 hydrogens to 1 oxygen, right? No matter what, whereas hydrogen peroxide is 2 hydrogens to 2 oxygens. So it doesn't matter if I have a big bottle of hydrogen peroxide or a couple drops of hydrogen peroxide. It's still 2 to 2, whereas water, I could have a big bottle or a drop, it's 2 to 1, okay? So law of multiple proportion just means that you can have more than one compound with the same elements in them. But the ratio is what makes them, that definite ratio, this fixed definite ratio is what makes them the compound they are. So here's some other examples. You got carbon monoxide versus carbon dioxide, right? So that's CO versus CO2. So both of them have carbon and oxygen. Carbon monoxide is 1 to 1, whereas carbon dioxide is 2 to 1, right? So those are multiple proportions. So there's multiple options with how carbon and oxygen can be combined together. And then here's an example of a whole bunch of different ones for nitrogen and oxygen or whatever. But generally, so definite proportions is talking about one specific compound. Multiple proportions is comparing different compounds with the same elements in them. So they're pretty easy to understand. All right. So when we look at a chemical compound, right? The percent composition always has to remain the same. And so this is due to what we just talked about. This always has to be the same, and this is the law of definite proportions. So we can use, and pretend I'm writing definite proportions a little neater, but whatever. You heard me say it, and you can spell it, and whatever. All right, so when we're doing an experiment, we can identify a substance, a compound, based on its percent of each element within the compound, because that percent is based on a definite proportion of what we know those elements have to be, okay? So percent composition is really easy. Usually there's different ways to calculate percent compositions, but we are going to do them by mass because it's the easiest, okay? So that means we're going to need our periodic table. You're going to need some molar masses, but they're really easy, okay? So here's an example of sodium dichromate. So with sodium dichromate, the formula, I know it's hard to see, Na2Cr2O7. So in this formula, we can look at what percent each element is of the total. The way we calculate it is really easy. It's taking the mass of that element divided by your mass of your compound. So anything that is a percentage, right, is taking the part out of the whole. And then we make it the percentage. That would be a decimal, and so it would be times 100 to make the number nicer, right? So in this case, our part is the element that is part of the whole compound, okay? So we can calculate the percent composition of an element or compounds And then later we'll talk about going the other way. How do we identify what elements are or what compounds are based on their percentages? So there's different ways to do this. But calculating a percent composition is really simple. And the percent composition should always be the same if it's the same compound, okay? So calculate the percent composition of each element in the formula of sodium dichromate. So we have the formula up here, right? So we're going to figure out how did they get those percentages. So in the example, the first thing you need to do is break it down into each element that makes it up. So we will break apart polyatomic ions into their individual elements as well. So you've got sodium, and you've got chromium, and you've got oxygen. And then the next thing to do is to look at how many of each there are, right? So I've got 2 sodiums, I've got 2 chromiums, and I've got 7 oxygens. All right, so in the formula, that's what I got. Then what we want to do is we want to look at find the total mass, because when we want percent composition, it's going to be based on mass. So you're going to look on your formula chart at the molar mass of sodium. And so when you look at that, I'm going to pull mine over here so I can make sure I give you the numbers. So on the formula chart I gave you, it's going to be 22.99 grams per mole. For chromium, it's going to be 52.00 grams per mole. And for oxygen, it's 16.00 grams per mole. So that is the molar mass of 1, but we have more than 1. So we're going to calculate that out. So we're going to take 2 times 22.99. It would help if I put that in my calculator correctly. And that's going to give me 45.98 total grams per mole for sodium. Everybody okay? Then we're going to take 2 times 52, which is going to give me 104.00 grams per mole mass-wise for the chromium in the compound. And then 7 times 16, you can probably do that in your head, but I can't, 112 grams per mole, okay, of oxygen. So then to find a percentage, we need to find the whole mass. So we're just going to add all those up because we want the whole mass of the whole compound. So if I add up 45.98 plus 104 plus 112, I get 261.98 grams per mole of the whole thing, right? Na2Cr2O7. So a percentage is super easy. So to set up your percentage, I'm just going to scroll over here because I write a little bigger when I do this. Your percentage is really easy. So you're going to find the percent of each one. So to find the percent of sodium, you're going to do 45.98 grams per mole divided by 261.98 grams per mole. And then we multiply it by 100 to make it a nicer number. So 45.98 divided by my 261.98 times 100. And I'm just going to give it one decimal place. We don't really hit sig figs real hard on this, so don't really worry as much about your sig figs. So 17.6%. If we go back up here to the chart, oh look, that's what we got, okay? Same scenario for my chromium. I'm going to take 104.00 grams per mole of the chromium divided by, that's my part, out of the whole, 261.98 grams per mole. Multiply that by 100. And if I'm pretty confident that I did it correctly, what I can do, so this one I get 39.7%. Let's check. Oh, look, I got the same thing. Okay, if I'm pretty confident I can actually, that I did those correctly, I could avoid doing this last one by adding them up because they should all add up to one whole pie or 100%. Or you can just go ahead and calculate it, 112 grams per mole. I would probably want you to show your work on like a quiz or a test to show me that you got them just for the one. But in real life, like for quick purposes or whatever, plug that in, you get 42.7%. So then you have your percent of each element that is making up that compound. So according to the law of definite proportions, that percentage can never change. It's always going to be the same. All right. So that's really all percent composition is. is it's a way to look at your overall compound and be able to realize that that compound percentage of those elements is based on their ratios, which is never going to change, all right? So what I want you to do before you turn in your notes is I want you to write the formulas and do both of those problems. So I want you to calculate the composition of each element in each of those problems. Then I want you to submit your notes. So actually try them and see how you do. And then if you have any questions, come to class and ask. But overall, not too bad. Make sure you don't have to show me all the molar mass work that you took 2 times unless you just feel like you need to do it. Really, what I'm looking for when I'm grading these is this portion right here. Okay, so I'm really looking for that. But you can, like sometimes students will do the example problem I have here. They'll take this and then they'll just take that and put divided by, I'm okay with that too. 261, like I'm okay with it doing it that way too. Grams per mole, because I understand that you would divide each one by that. So I know that that's where those numbers came from. So either one, but I don't need to see individual that you took 2 times 22.99, 2 times 52. I would assume that you know how to do that if you get the right answer. So if you're getting the right number on top for the element. So, but I showed you that so you had it just in case. All right. So make sure you show your works on those. Don't just give me percentages, but otherwise you should be good. Come to class with any questions.